Good evening, students. So in the previous video we discussed this textbook up to this paragraph where we have seen the sp3, sp2 and sp hybridizations with examples like methane, ethene and ethine respectively, and their characteristic properties also we discussed up to this paragraph. So that link I will give in this video and you can go through it. Now in this video the next topic of our discussion is some characteristic features of pi bonds. So here pi bond, in a pi bond formation, parallel orientation of the two p orbitals and adjacent atoms is necessary. So that is what we discussed in sp2 hybridization. Here in the case of sp2 hybridization, here we discussed taking the example of ethene. So the same thing, parallel orientation of the two p orbitals and adjacent atoms is necessary. That's what we discussed in the sp2 hybridization. That is for a proper side wave overlap. So what he is telling, thus in CH2 double bond CH2 molecule, all the atoms must be in the same plane. That's why sp2 hybridized carbon is having planar structure. sp2 hybridized carbon is having planar structure, trigonal planar structure. That is why all the atoms are in the same plane. Okay, the p orbitals are mutually parallel and both the p orbitals are perpendicular to plane of the molecule. This also we discussed. So here once again I recollect that one whatever we discussed in the sp2 hybridization in the previous videos. So what he is saying is here, so sp2 hybridized carbon is having 3 sp2 hybridized carbons, 3 sp2 hybrid orbitals. Each sp2 hybridized carbon is having 3 sp2 hybrid orbitals. That's what I explained in the previous videos, that you can go through. And those 3 p orbitals will be arranged like this. This is one sp2 hybrid orbital, this is another one sp2 hybrid orbital, and this is another one sp2 hybrid orbital. These are the 3 sp2 hybrid orbitals. And for another sideway carbon, this is one sp2 hybrid orbital, this is another sp2 hybrid orbital, this is another sp2 hybrid orbitals. So now two p orbitals, so all these, this is one carbon, this is one carbon. So here one hydrogen will be there, hydrogen will be there, here another hydrogen will be there, here another hydrogen will be there, two electrons, one electron from sp2 hybrid orbital, another electron from hydrogen. This is hydrogen, this is hydrogen, this is hydrogen, hydrogen, spherical shapes, and 4 hydrogens are bonded. This is carbon, this is carbon, that means this is carbon, this is sigma bond, and this is hydrogen, this is hydrogen, this is hydrogen, this is hydrogen. So like this the structure looks like this. So generally we write like this, but actually in orbital model of structure orbitals will be arranged like this. So this is what he is saying. So what he is saying, in a pi bond formation, parallel orientation of the two p orbitals on adjacent atoms is necessary for a proper side wave overlap. So this is what the framework of the two carbons, this carbon, and now the two p orbitals are arranged here. This is one p orbital, this is another p orbital, unhybridized orbital. So these two are parallel, little bit more. So these two are parallel to each other. Here one electron will be there, here one electron will be there. So this is called side wave, lateral overlap, side wave overlap, above and below, above and below. That means that is simply represented by just a bond like this. So this bond, pi bond, this is called pi bond. This above and below, whatever sideway overlap is there, that is called pi bond. That one. And this bond is represented here. This one, sigma bond. This bond is represented here, sigma bond. This is sigma bond. This is also sigma bond. This is also sigma bond. In ethene, 4 sigma bonds are available and 1 pi bond is available. So here necessary for a proper sideway overlap. Okay, so proper sideway overlap here. So proper sideway overlap, both the p orbitals are exactly parallel for proper sideway overlap. Thus in CH2 double bond CH2 molecule, this CH2 molecule, all the atoms must be in the same plane. Here all the atoms are touching the paper. All the atoms, hydrogen, this carbon, this hydrogen, all the hydrogens are touching the paper. Okay, that is not possible in tetrahedral structure because this is planar trigonal structure. Planar trigonal structure, all the atoms are in the plane. Okay, the p orbitals are mutually parallel and both the p orbitals are perpendicular to the plane of the molecule. So here these 3 orbitals are on the plane, and like in the previous video I explained, this orbital is just like perpendicular, like this, perpendicular, like this is paper to the paper, it is perpendicular, exactly like this, perpendicular. So this is exactly perpendicular to the plane, 90 degrees. This one also exactly perpendicular like this to the plane. So the p orbitals are mutually parallel and both the p orbitals perpendicular to plane of the molecule. Rotation of one CH2 fragment with respect to other interferes with maximum overlap of p orbitals. So what he is saying is, here if you see, it is like this bond and this bond both are same bond, that is nothing but a electron density above and below the plane, electron density. So here also tied up, here also tied up, above and below it is tied up, electron density is tied up. So that means this orbital cannot be rotated, so like this cannot be, it cannot be like this, it cannot be rotated, or it cannot be rotated like this, it cannot be rotated. Why? Because above and below both are tied up. Okay, so the p orbitals are mutually parallel and both the p orbitals perpendicular to plane of the molecule. Rotation of one CH2 fragment with respect to other interferes with maximum overlap of p orbitals, and therefore such rotation about carbon-carbon double bond is restricted. That means double bonds and triple bonds are not not able to rotate. That means they are restricted rotation. They have restricted rotation. That means they don't have any rotation. They fixed like this. They fixed, though they cannot be rotated like this. But single bond can be rotated. Single bond is like this, so it can be rotated freely like this. But double bonds are like this, so they cannot be rotated. Okay. The electron charge cloud of the pi bond is located above and below the plane of the bonding. So here this is electron, this is electron. So like this line we represented, but actually it is like a cloud, electron cloud here, electron cloud here. So both are having attraction. This p orbital, both are having attraction above and below the plane. So this electron is having attraction with the nucleus, this electron is having attraction with the nucleus. So we represent a little bigger, but actually atom means it is very, very small. So electron density is spread around very nearer. So it is restricted. Okay. Amount below the plane of the bonding atom. This results in the electrons being easily available to the attacking reagents. This results in the electrons being easily available to the attacking reagent. So here pi bonds are labile bonds. So here sigma bonds are very strong bonds. This sigma bond is very strong bond. So here axial overlap is there. Here lateral overlap is there. Pi bonds are labile bonds, means if any electrophile comes, so this electron, these are having negative charge. Negative charge. If any electrophile comes, electrophile means positively charged species like CH3 plus or Br plus. So this kind of positively charged species comes, then this electron density attacks this bromonium ion or methyl carbonium ion. That means methyl carbocation. Carbonium ion or carbocation but are same. So that is what he is saying. This results in the electrons being easily available to the attacking reagents. This is reagent. These are reagent. So these electrons easily attack these carbonium ions or bromonium ions or nitro ions, like that, positively charged species. In general, pi bonds provide the most reactive centers in the molecules containing multiple bonds. That means if in a molecule, if pi bond is there, like double bond or triple bond, this is nothing. So triple bond, this here two pi bonds are there, one sigma bond is there. Here one pi bond is, one sigma bond is there. So these kind of bonds will attack this means reactive intermediates easily. That means this electron density is available for reactions, for changing in the molecule, reactions in the molecule. So that is what it is. Okay, this is what some characteristic features of pi bonds. Okay, so now here some problem is there. 12.1, 12th is chapter name, one is question name. How many sigma and pi bonds are present in the each of the following molecules? Here two molecules are given. Let us see how many sigma and pi bonds are available. I am writing here those molecule structures here. This is CH triple bond, C, CH double bond, CH, CH3. This is what he is given. Okay, this is what the molecule, first molecule is given. The second molecule, this is A. So the second molecule given is CH2 double bond, C double bond, CH, CH3. This one, these two molecules are given. Now he is asking how many sigma and pi bonds are present in the each of the following molecules, two molecules. So let us see this molecule. So we have to expand it. A, this one, A, we have to expand CH, C, H. So triple bond is there, triple bond is there, C, C. Here C, C bond is there, C. The H is there, H we have to write like this. C, C, H. Here double bond is there. Here CH, C, H. Here CH3, CH3. Like this we have to represent that one. Like this we have to expand that structure. So here C, he has not given, they have not given any bond in between this, but there is single bond C, H. Here triple bond, this C is there, this C, and C, C in between bond is there. Here C, H, C, H, double bond. So C, this H is bonded to the carbon and this CH3 is bonded to CH3, like this. Okay, now let us see how many sigma bonds are available. This is one sigma bond, one. In this triple bond, one is sigma bond. Here in double bond, one is sigma bond. So we can expand these three also. Here that means these three are sigma bonds. These three also sigma bonds. So let us see sigma cc, sigma cc, and sigma ch, and pi uh, double bond, pi triple bond. So sigma cc single bond, this is 1, this is 1, 2, 3, 4. 4 are there. 4 sigma cc single bonds are available. 4. So sigma ch, this is 1, 2, 3, here 3 hydrogen, 4, 5, 6. That means sigma ch is 6. Here pi double bond. Here 1 pi bond is there. Pi double bond. That means this is 1 pi bond. 1 is there. Pi here triple bond. That means these two are triple bond. So that is 1 is there. In this triple bond, 2 pi bonds are there. 2 pi bonds. So cc, sigma cc are 4, sigma ch is 6, pi in this double bond 1 pi bond is there, in this triple bond 2 pi bonds are there. That means total sigma bonds are 10, total pi bonds are 3. Total sigma bonds are 10, total pi bonds are 3. So in this triple bond 1, 2, double bond 1. So 3 pi bonds are available and 10 sigma bonds are available. So like that we can answer this question, the first one. And the second one, if we see that one, so B CH2, here H, here H, this one double bond. I am expanding this C and double bond. This C, H is like this, and here C H H H. I expanded that one. Okay. Now CC sigma bonds, sigma CC, CC, and sigma CH, and pi C double bond C. Okay. So here CC sigma bond, this one 1, this one 2, this one 3. 3 are there. Okay. So CH, this is 1, 2, 3, 4, 5, 6. 6 are there. And pi, so this is 1 pi bond, this is 1 pi bond, this one and this one, 2 are there. That means total sigma bonds are this one and this one 9. Total pi bonds are 2. So sigma bonds are 9 and pi bonds are 2. So like that we can complete that question. Okay. Okay. So we'll stop here, and next question we will see in the next class. Thank you.